Alright, for this video, we are going to continue with heat transfer by conduction through cylinder. In previous video, you have been introduced with the terms that is going to be used throughout this particular chapter. So now we are going to go deeper into the heat transfer by conduction through cylinder. So frequently, heat will pass through several consecutive layers of different material. For example, in cold store, the heat might pass through brick, plaster, wood and cork. Okay, this is the built-up material for the cold store because it must make sure that the temperature inside of the chiller room is cold. So that's why it needs to have several layers of material. Okay, we assume in steady state, the same quantity of heat per unit time must pass through each layer. Alright, so can you see this equation? This one Q equals to Q, the equation for Q again, Q equals to Ka delta T over X. Alright, so Q, if let's say I have three materials here, Q for material number 1 must be the same value for material number 2, must be the same for the Q value for material number 3. Meaning that Q equals to Q1, this one Q1, equals to Q2 equals to Q3. Okay, and Q, the equation for Q is Ka delta T over X. So from here, Q for material number 1 must be similar with Q for material number 2, must be similar for Q for material number 3. Alright, so let's take example. Let's assume that the area are at the same area. For area 1 is equivalent to area 2 is equivalent to area 3. Then we can denote the area as A. Okay, this one A1, A2, A3. They are having the same value. So you can just use as A. You do not need to differentiate between this area because they are having the same area, the same size of area. Okay, so when we simplify again this equation, it becomes Q equals to Q1, the area is the same with the material number 2 with the same with the value of area material number 3. Alright? Okay, and then we rearrange the equation. The A delta T1 equals to Q x1 over K1 because this particular x1 over k1, this one related with the conductance. Alright, and then A delta T2 equals to Q x2 over k2, and A delta T3 equals to Q x3 over k3. Alright, since we are going to look for the heat transfer through series, okay, series meaning that they have several material, so the sum of the Q, when you rearrange this one, so A delta T1 plus A delta T2 plus A delta T3 equals to Q x1 over K1 plus Q x2 over K2 plus Q x3 over K3, depending on how many materials that we are going to deal with. Okay, then since the area for the calculation of heat transfer are at the same value, so you can take out the area and then just sum up with delta T. Okay, the value of delta T equals to Q, alright, x1, because the value for the Q is the same value as well. So x1 over k1 plus x2 over k2 plus x3 over k3. Okay, so this one is meant for the rearrangement of the equation when we are going to deal with the layers. Alright, sum of temperature difference over each layer, look at the top part here, sum of temperature difference over each layer is equivalent to difference in temperature of two outside surfaces of complete system. Okay, that is delta T1. This one, where does it come from? It comes from this particular part, this part. Okay, so delta T1 plus delta T2 plus delta T3 equivalent to delta T. Okay, what does this mean? Alright, so this one, for example, I have a material consists of 3 materials, so I draw it here. Okay, for example, the heat is being flown from your right to your left, alright? And basically, when we want to measure the temperature, we will measure the temperature at the wall of the material. Okay, so this one is T1. Okay, this one is T2, material 2. This one is T3. This one is T4. Okay, at this part. T4. Alright, so starting from your right hand side, for example, this particular temperature is at 80 degrees Celsius. 80 degrees Celsius. Okay, and then the exit temperature is 20 degrees Celsius. 20 degrees Celsius. And in between this temperature, for example, T2, T2 is 65. T3 is 45 degrees Celsius. Okay, so it starts from 80 degrees Celsius, and in between for T2 the temperature is 65 degrees Celsius, T3 is 45 degrees Celsius, and then the surface of T4, this one is 20 degrees Celsius. Okay, so from here, delta T is the sum of temperature difference. Okay, can you see this one is the symbol for sum of temperature difference between T1 minus by T2 plus T2 minus by T3 plus T3 minus by T4. Okay, so plug in the value sum of T1 minus by T2, 80 minus by 65. Okay, plus T2 minus by T3, this one 65 minus by 45, plus this one T3 minus by T4 is 45 minus by 20. Alright, so calculate the answer. You should be able to get delta T equals to 20 degrees Celsius, the sum of this temperature difference. Alright, so this is what does it mean. But what does this particular statement means? This whole statement, okay, sum of temperature difference over each layer of material is equivalent to difference in temperature of two outside surfaces of complete system. Two outside surfaces meaning that for T1 is outside surface, T4 is another outside surface. So how do you want to calculate this delta T? By using this particular statement is whereby you can simplify delta T as by T1 minus by T4. Okay, so can you get this one is not 20 degrees Celsius. Okay, this area, this sum of temperature difference is 60 degrees Celsius. Okay, please make changes for this one, 60 degrees Celsius. So temperature difference between two outside surfaces is simply by you need to subtract between T1 minus by T4. T1 is 80 degrees Celsius minus with 20 degrees Celsius. So you will get still the same answer as 60 degrees Celsius. Can you get this one? So this, what does it mean? Sum of temperature difference over each layer, this one, is equivalent to difference in temperature of two outside surfaces for complete system. Okay? Alright, so now let's move on. Since K1 over X1 is the conductance, alright? This one refer back at this one. K over X is conductance. Okay, K over X is conductance material for the first layer. Second layer is K2 over X2. So we rearrange the equation. It becomes X1 over K1 plus X2 over K2 plus X3 over K3. This one coming from previous slide. Okay, this one equivalent to 1 over C1 plus 1 over C2 plus 1 over C3. Why it becomes 1 over C1? Because conductance is being the equation for conductance is K over X. But what we have here is X over K. So this one is 1, for example, 1 over X over K. So when you rearrange this equation, it will become K over X, because this particular K you need to put it at the upper part. Okay, this one you have learned the mathematics, additional mathematics or modern mathematics during your high school years. Alright, so the sum of this 1 over C1, 1 over C2, 1 over C3, this one can be quantified as 1 over U, whereby U is the overall conductance for combined layers. Okay, this particular U is conductance for combined layers. So since we have this Q times by 1 over U equals to A delta T, then we arrange back in order to get this particular Q equals to UA delta T, and U is overall heat transfer coefficient. And okay, this one I explained to you how to derive this particular equation, how this particular equation is being derived. So in order for you to use for the calculation, you just need to use this particular equation. Okay, the explanation that I have explained to you, that one just to let you know how this particular equation is being derived. Okay, but then you need to make sure that you understand this particular delta T. Okay, so estimation of overall heat transfer coefficient through cylinder. Alright, this one, how to calculate for the heat transfer through cylinder. Heat transfer in a pipe that carries a fluid at a temperature greater than temperature of the environment surrounding of the outside of the pipe. So for overall heat transfer, this one we have derived just now. The equation is Q equals to UA delta T. Okay, and then Q equals to, correct, from equation number 1, we can rearrange, the equation becomes Q equals to delta T over 1 per UA. Because this one again, when we rearrange the equation, you will still able to get Q equals to UA delta T. Alright, but this one, when it involves with the cylinder, we need to calculate for the value for the A. Okay, so from this particular equation, we put it here. Alright, Q equals to delta T over 1 per HIAI, I is heat transfer coefficient for the inner part, plus ln R0 over Ri. R, why you need to deal with R? Because we have the diameter of the cylinder, so you need to calculate for the radius. Okay, divide by another A, okay, 2 pi Lk, plus by 1 over H0 A0. H0 is the outer heat transfer coefficient, A0 is the area for the outer part of the tubing of the cylinder. So let's simplify this equation. In the next slide, we rearrange the equation. Just plug out the 1 per UIAI. UIAI equals to 1 over HIAI plus ln R naught per Ri over 2 pi Lk. Okay, this one we just want to get this particular value, 1 over U. Okay, so since U naught is selected as the overall heat transfer based on the outside area of the pipe, so 1 over UIAI equals to 1 per HIAI plus ln R naught over Ri per 2 pi Lk plus 1 over H naught A naught. Okay, now please take a look for this particular equation because we are going to select for U naught. So this particular equation, you need to do some correction. This one supposed to be U naught. Okay, this one is U naught, this one is A naught for the outer pipe. Equals to 1 over HIAI plus ln R naught over Ri per 2 pi Lk plus 1 over H naught A naught. So by cancelling area, because this one is A naught, okay, can be cancelled with this one A naught as well. So by cancelling area terms, and you need to note that A naught, the area, when we want to calculate for the area is 2 pi R naught L. Okay, this is how you want to calculate the area for cylinder, 2 pi R naught L. When we talk about the outer area, okay, you need to use the radius for the outer area. It must be in pair together. You cannot use, when you have A naught, you use 2 pi R I L. This one is wrong because this is not the radius for to calculate for the outer part of the area. Okay? Alright, so I have did it just now. So make sure that A naught should be in pair with R naught. Alright, so we rearrange this equation. So it becomes 1 over U naught equals to R naught per HIRI plus R naught ln R naught over Ri per K plus 1 over H naught. So this particular equation need to be used when we are going to calculate for the value of U. Okay, so this particular equation you need to memorize. Alright, you need to practice. Try to write the equation. 1 over U equals to, is the same thing. Whether you want to put here at the front or at the back, it is the same thing. 1 over U equals to 1 per H naught plus R naught ln R naught over Ri divided by K plus R naught over Ri/Hi. Alright, you need to try to write this equation many times so that you will be able to automatically, your cell will have their own memory and they will help you to write it out for you. Okay, so when you write this equation many times, then you eventually will memorize it on your own. Okay, you don't have to struggle of how to memorize. You just need to keep on writing of this particular equation. Keep on writing 1 over H naught plus R naught ln R naught over Ri per K plus R naught over Ri/Hi. Try to write this one many times so that your body is having their own memory to write down this particular equation. Alright, so this is the equation that I mentioned to you just now that you need to memorize. Okay, so when you have the 1 over U, when you have calculated, that's not the end of your answer, because 1 over U, for example, the value is around 10. For example, this particular value is 10 for 1 over U. You need to calculate for the U. U is, how do you want to calculate for the U? U is 1 over 10. Okay, so it becomes 0.1. Okay, the unit is, what is the unit? So you need to ensure the unit is correct as well. Okay, so U is what that we want. U is what we are interested in. So U is overall heat transfer coefficient, because when you are able to calculate for the U, then you can plug in this particular value into the equation of Q equals to UA delta T. This one, you are going to calculate rate of heat transfer in cylinder. Right? Where A, okay, A cross-section area measured perpendicularly to the direction of the flow of the heat, whereby you need to use the equation of A as 2 pi R naught L. L is the length. L is the length, the unit is in meter, R naught is R naught. So when we talk about A, this one representing for A naught, okay? Outer part, the outer area, 2 pi R naught L. If you are going to calculate for inner AI, so you need to use equation 2 pi R I L. Okay? Please make sure that this particular I must come together with the I. If this is A naught, it must come together with the R naught. Okay? Now we move on to heat transfer by conduction through composite wall. Composite wall, this one is a rather simpler compared to the cylinder, because the equation is very straightforward. For example, we have composite wall, the thermal conductivity, it can, since it is composite wall, so thermal conductivity must be coming from several materials, of material 1, material 2, material 3, and thermal conductivity is being denoted by K. Okay, the unit is watt per meter Kelvin. Thickness of the walls are X, alright, depending on the quantity of material that you are going to deal with in the composite wall. And again, the unit for the thickness is in meter. Then followed by temperature difference between surface of walls, between wall 1 and wall 2. So delta T is T1 minus by T2. Alright, now, again, let's refresh your memory. Again, this one, delta T is in degree Celsius, but the thermal conductivity is in Kelvin. Do you need to convert the value of temperature in degree Celsius to Kelvin? Yes or no? It is not necessary. Not necessary. If you have extra time, you can calculate, but if you don't have extra time, then you do not need to convert. But if let's say the temperature in degree Fahrenheit, delta T in degree Fahrenheit, it is not equivalent with delta T in degree Celsius. Alright, it is also not equivalent with delta T in Kelvin. But delta T in degree Celsius, they are having the same value as delta T in Kelvin. Okay, do you get that? Okay, this one delta T in degree Fahrenheit. Okay? Alright, so when we talk about several materials, when we talk about the material in the composite wall, so of course you are going to deal with several materials, the one that I've drawn just now. For example, I have this a slab containing of several material. Okay, for example, this one is a brick, this one is wood, and this one is cork. Alright, so we have three materials. So you need to use the equation Q equals to UA delta T. But in order for you to calculate for the U, because U is the overall thermal conductance, overall heat transfer coefficient. So in order for you to calculate for the U, you need to use the equation 1 over U equals to X1 over K1 plus X2 over K2 plus X3 over K3. Okay, this one is meant for composite wall. Alright, because it has the thickness, it has the thermal conductivity. Do not use the equation that is similar for the cylinder, because cylinder is different compared to composite wall. Alright, so for composite wall is very much simpler compared to the heat transfer through cylinder. Okay, so rate of heat transfer Q equals to UA delta T, where A equals to cross-section area measured perpendicularly to the direction of the flow for the heat. Alright, now let's move on to the problems of heat transfer by conduction. For the first problem statement, this one is meant for the cylinder. Alright, so calculate the rate of heat transfer for the tube heat exchanger with inner and outer heat transfer coefficient of 580 watt per meter square Kelvin and 5750 watt per meter square Kelvin respectively. The temperatures of inner and outer surfaces are 95 degrees Celsius and 30 degrees Celsius respectively. Thermal conductivity of the tube wall is 55.5 watt per meter Kelvin. The diameter, the thickness and the length of the tube are 2.2 cm, 1.6 mm and 1 meter respectively. Okay, so what you need to do for this particular problem statement? It has been stated in the first statement. Calculate the rate of heat transfer. Okay, calculate the rate of heat transfer, meaning you need to calculate for this one, you need to calculate for the value of Q. Okay, then when you read along, it is tube heat exchanger with inner and outer heat transfer coefficient, meaning that this one is a series. This one is heat transfer in series. So 581, when we have the word respectively, so 580, this one is meant for the inner. Okay, and then 5750, this one is for the outer. Alright, and what is the denotion that is being used for the heat transfer coefficient? So this one inner is H0, Hi, 5750, this one is H0. Okay, and the temperature of inner and outer surfaces, inner T1 95 degrees Celsius and outer, this one is T2 30 degrees Celsius. Thermal conductivity are given, this one is the value for K. Okay, the diameter is 2.2 cm, so this one is D, diameter. Alright, and then thickness, this one is X, and the length is 1 meter. Okay, but do you notice that this particular unit of the diameter, thickness and length are being given in 3 different units? One is centimeter, one is millimeter, and the other one is meter. Do you notice that? So when you notice this one, you need to make sure, first thing first, what you need to do is you need to convert these units into one SI unit only, so that you are not going to confuse yourself. So this particular 2.2 you need to convert to become meter. This millimeter you need to convert to become meter as well. Alright, of course this 1 meter, then you just leave it as it is. Okay, so what you need to do is you need to use the equation of Q equals to UA delta T. And since we are going to deal with cylinder, then you need to use the equation of 1U equals to 1 over H0 plus R0 times by ln R0 over Ri, okay, per with K plus R0 per Ri Hi. Alright, so do not confuse yourself with this R0, where to put this R0, where to put the Ri, H0 and etc. You need to practice of how to write this particular equation. Alright, so now this is the photos of the U-tube heat exchanger. Okay, this one is the U-tube, this one is the straight tube heat exchanger. Okay, so how to answer this particular problem statement is whereby you need to gather and list out the information that is given. Okay, so the first thing first, for the diameter given is 2.2 centimeter. So what you need to do is you need to convert to meter. Okay, over here, meter. So since this one is diameter, you need to calculate for the radius. So how do you want to calculate for the radius? Okay, Ri equals to diameter di divided by 2. So you will be able to get Ri. Alright, and then in terms of the thickness, it is given in 1.6 millimeter. So you need to convert to become meter. Okay, 0.0016. Okay, and then R naught, how to get the value for R naught? Alright, so again, I draw this one for you. For example, I have the tubing. Okay. So from the center to this part, this one is Ri. In between this to here, this one is the thickness. So from here to here is R naught. So R naught equals to Ri plus X. Alright. So that's why you get R naught equals to 0.0126 meter. Whereby from the inner radius plus with the thickness. So you should be able to get R naught as 0.0126 meter. The length has been given 1 meter. H naught is 5750. Hi is 580 watt per meter square Kelvin. K is 55.5 watt per meter Kelvin, and delta T, this one is 95 minus by 30. This one already given from the problem statement, so you can just simply by calculating the value of temperature difference, and it is 65 degrees Celsius. Okay, so apply the equation of 1 over U equals to 1 over H naught plus R naught ln R naught over Ri per K plus R naught over Ri Hi. Just plug in all the value that you have calculated at this particular part at the top. Okay, plug in all the values, and then you should be able to get as 1 over U as 2.17 times by 10 to the power of negative 3. Okay, but you need to calculate for U. Okay, you need to calculate for the U. So how are you going to calculate? It will become 1 over, so U equals to 1 over 2.17 times by 10 to the power of negative 3. So you should be able to get this particular value, and the unit is in, alright, so this one equals to U equals to 460.83 joule per meter square second degree Celsius, or look back, okay, why joule per meter square second degree Celsius? Because this one, if you look at the temperature conversion, 1 watt equals to 1 joule per second. So basically just use back this particular value. Okay, U equals to 460.83 watt per meter square degree Celsius. They carry the same meaning. Okay, this one, they carry the same meaning. And then after that, calculate the value for the A. A is 2 pi R naught L. We take as R naught for this A naught. Alright, and then plug in the value, and you should be able to get this one. And please add the unit here, supposed to be meter square. Okay, the value of area is 0.0792 meter square. Okay, and then use the equation Q equals to UA delta T from the value that you have calculated for the U. Okay, masukkan, please put here, and then the value for A, put it here, delta T you have calculated from here, put it in the equation as well, and then you should be able to get this particular answer. And this also, this joule per second, you can use as watt as well, right? Or you can simplify this one, Q equals to 2372.3528 watt. You need to know where to cancel the unit. Okay, which unit that you can cancel out, and it leaves at the end as which unit. Okay, so we are going to continue for next video. For the next example, please work on your own how to calculate for this particular problem statement, and I'll see you in next video.